Hi everyone and welcome to a new video about control systems topics, and we continue with the subject of stability. In the previous videos we have looked at several examples using the Routh-Hurwitz stability criterion to determine the stability of a closed system. Now in this video we will discuss the special cases. So let's first discuss this in more general form. So we have several special cases. Case 1 is when you have in your first column of your Routh table only one zero that can contain one zero. That is the first case. And the second case is that you have a entire row consists of zeros. That is also possible. So we will discuss this also using several examples. Now in case 1, the first column contains only one zero. That means you need to make a division by 0, which is undefined. So it will be required. And that is a problem, so you need to tackle this. For example, if you have this characteristic equation, which is shown here in the third order system with these coefficients. If I now use a table, Routh table, and I substitute the values and I calculate the B1, etc., what you see is B1 is now equal to 0. Now, if this is 0, the next step to calculate C1 will require B1, and you divide them by B1. So that will mean in the following step that you have an error. So you need to analyze this in a different form. Now for that, we can use, again the table shows the error. So for that we can assign a positive value to replace a small positive value to replace that 0, and that's just a name. We call this an epsilon. You can also call it another symbol, and that will be used to evaluate the rest of the elements in your Routh table. Now this epsilon is allowed to approach 0 either from a positive or a negative side, so that will be also clear when we discuss the examples. Now in case 2 you have an entire row of zeros. So for example, if you have this system, which is a fifth order system, it can have a row with only 0. So this is a general table again for the fifth order system. If you now do the math for the B1, B2, B3, etc. So let's first start with the B1s. And that's again the familiar formula we have discussed in the previous videos in more detail. Now B2 and B3, what you see is all of the B's are 0. So you get a table with a row which consists of the 0. So that is the case 2 in this case. So if you have this, that is just shown here, we can tackle this also in a very specific form. And that will be also discussed in the example. So we have now here an entire row of zeros. So having these zeros means actually that you have a couple of roots with equal magnitude and lying radially opposite in the S-plane. And that can be, of course, two real roots, but with equal magnitude but opposite signs. So it can be, for example, you have a -6 and a +6. That is a possibility. It can also have that you have two conjugate imaginary roots, so that you have then a pure oscillation for your output signal. Now, we will use a special polynomial which is called auxiliary polynomial to evaluate the elements for our Routh table. So this will be shortly replaced by using this auxiliary polynomial, and then we can carry out our following steps to determine the stability. Now let's look at the example, and then we start with the first case, special case 1, and we use there the epsilon method. We have also another method. I will discuss this shortly in the next example. Let's look at the situation. What we have is the following. Determine if the closed-loop system TS, which is shown here, is stable. Now we have now a third order system, we have the coefficients. Now let's first again begin with step 1 is determine the characteristic equation of this closed-loop system. Now the characteristic equation of this system is given by its denominator, and that is equated to 0, as you can see here, which is the denominator here. Okay, we have now this characteristic equation. If I now go to the Routh table, generating the Routh table, this is the general expression for the third order system. This is our characteristic equation, and these are the coefficients. So we need all of them to set up our Routh table. So if I now have the general form of a third order system, and I substitute the values after calculating B1 and B2, B3, etc., what you have is B1 is 0, and that results now again in C1 is error. So you will see here that again we have a B1 is 0. That means that we have the situation with a 0, 1, 0 in the first column. That is the case 1. Now we need to tackle this, and we will use the Epsilon method for this problem. So the Epsilon method says the following. The step 3 is replace the 0 with a small value, small number, and we call this just an epsilon. So that means you replace a 0 by an epsilon, and you carry out actually the same calculation for B1, B2, etc. So if I now do the math again, I say just B1 is epsilon, then B2 is this formula you use again as we did in the previous videos, and you will get a 0 for B2. B3 will result also in 0 in a similar form. But C1 now uses, of course, the B1, which is now an epsilon. If you now look at the expressions using also the B1, we have now determined here for the C1 calculation, you will see that you have here 12 epsilon, and you divide by epsilon, you will get exactly 12. That means actually new table have now epsilon in it, and the last term here, the element is 12. So you will now look again at this first column to determine your stability. Now we already said that this is a very small value, the epsilon. So if I now let it approach to 0, I have the following new table. Now if I look at this table, and I don't want any sign changes to have a stable system, I have now a plus and again a plus. This is 0, and this is also plus. So this means actually, since you have a 0 here in your first row, that means actually that you have a marginally stable system. The conclusion is actually that this system will oscillate for this condition, and that you have two conjugate imaginary roots. Now, since this is a third order system, there must be also one root in the left half plane. It cannot be in the right half plane, because this system is not unstable. It is marginally stable, so the rest of the poles must be in the left half plane. That's actually for this example. We will solve this example. We can also solve this example using another method, which is called the reverse coefficients. But I will now discuss another example, and we will use it also with the epsilon method, and we will now also do that with another method. So let's look at another example using the epsilon method again. Now we have this transfer function. Again, carry out the analysis using step 1, determine the characteristic equation, looking actually in the denominator of this transfer function, equated at 0 as shown here. You develop again your Routh table with the coefficients for the third order system. Look carefully, you have a s squared here, and then minus 3s, s cubed. So the s squared term is not presented. That means actually that a2 is 0. So a3 is 1, the coefficient in front of the s cubed. S squared, there is no s squared, so that means actually that it's 0. There is the s, and in front of it is a minus 3. You will take the minus 3 for a1, and a0 is 2. So we have now the coefficient to set up our Routh table. Now that is general form of the third order system. If I now want to calculate the required values for this system, I get a B1, which is now 0, which is now an error. Why? Because the A2 is now the 0. So I already got the error 0 without any calculation for B1 and C1. So this system is already a 0, as you can see here. So we have already an error. That means I need to again use another method special. This is a special case, and we will use again the epsilon method. Now I will replace again the 0 with a very small number, an epsilon. So I will carry out again the calculation for B1, B2, etc. So if I now set this equal to epsilon, that is just A2 is epsilon. Now B1 will be again calculated, but then using, of course, A2 is an epsilon. So if I now do the math here, you will get minus 3 minus 2 over epsilon. Now B2 in a similar form, you will get exactly 0 here, and B3 also 0. And for C1, I will get 2. So if I now use all these new values and set up the table again, I have the following situation. I will again look at the first column to determine the stability, but this time we need to be very careful. Of course, this number can approach 0 from a negative or a positive side. So if I now set up a table for the first column and I evaluate that the epsilon is a little bit positive or a little bit negative, I can have the same conclusion. So I would like to demonstrate it also. So we have the label, which is the label here. We have the first column, which is actually just a copy of what we have here. If I now use the epsilon as positive, which is a positive number, this is the positive, so you will see only the positive and negative signs here. So this is positive, this will be positive. If I use epsilon as positive, that means 2 over the positive number will stay a positive number, but you have a minus and a minus, so that will be in total a minus sign. So there's a minus number, and this is just a positive. So I have now a positive, positive, negative, and a positive. So that means actually I have 2 sign changes. So from the positive to negative, from negative to positive. Now, for example, if the epsilon is not positive, but very small value, but negative, I can again carry out the same analysis. This is again positive, so this is just a plus sign here. But this is negative, so this is negative. Now, if I do the math here, again, 2 divided by a very negative number, but very small, this will be a positive. And if this is, of course, very small, then this minus 3 is actually insignificant. This will be then a positive value. So this is a positive, and this is also positive. So what you then have is now, from positive to negative, and from negative to the positive, you have again 2 sign changes. That means we have again the same conclusion, and this system, since there's at least 1 sign change, there is in this case 2 sign changes. That means actually that you have 2 roots in your right half plane, and this system is unstable. That's the conclusion for this example. I will now solve this problem, having the special case 1, for this transfer function using the reverse coefficient method. So I have again the same transfer function, but we will carry out this using another method. And this method can be sometimes handy, and most of the time it also requires less calculations. So let's again start with the characteristic equation. Again, the same procedure. We will take that. And that is the characteristic equation we need. Now, the step 2 is a little bit different. In addition, you need to form a new polynomial by writing the denominator of this original transfer function in a reverse order. That means actually the following. You start at the 0th term, and you make that actually the highest order term. So if I write it down, so ds will be now 2s cubed. And then this will be s squared, so minus 3s squared. And there is no second order term here, so I will skip that. And this term, which is now the highest term here, that will be the lowest term there, and you will just take the coefficient. So this is actually our new polynomial, and also the characteristic equation. Now we generate the root table using this reverse order polynomial. Now, again, the general form of our third order system. Let's calculate the values. B1 will be, again, using this and this, and this actually is A3, A2, A1 is not present there, and A0 is there. So we have the values here. If you now do the math, you'll get 2 over 3. Now B2 is just 0, and B3 is also 0. Now if I now do it also for C1, in a similar form, I get those three values. If I now substitute the values in the table now using this reverse order polynomial, I get the following table. As you can see, we haven't used any epsilon. We just reverse the coefficients, and then we have the exact same analysis as we did in the previous examples using the epsilon, without using the epsilon methods. Now, I will check again the first term, the first column, and I see two sign changes from positive to negative, from negative to positive. Again, the same conclusion, two sign changes. That means there are two roots in the right half plane. That means this system is for sure also unstable. So the conclusions are exactly the same. We have again two roots in the right half plane, and the system is unstable. But we carried out this exercise using a different method, which is called a reverse coefficient method. Now let's look at another example using then case 2. So let's look at the case 2 problem. Now determine if the closed-loop system TS is stable. This system, it's a fifth order system, it's a little bit complicated. Now what we have, again, we'll look at the characteristic equation. We develop this, just take this and set it equal to 0. Generate your row table using, of course, fifth order polynomial general formula, and you will have your fifth order characteristic equation. Just look at the coefficients or like terms. A5 is 1, A4 is 7, A3 is 6, A2 is 42, A1 is 8, and A0 is 56. So this is required for setting up our row table. This is a general table for our row table. And if I now calculate the required values, I will have B1 is 0, B2 is 0, B3 is 0. So that is actually the situation for where you have only zeros in your, there is a row with entire zero. So there's a row with only zeros. And that means actually that C1 will be a error. So I cannot carry out this calculation. So I need to tackle this in a different form. So this is a table and this is the problem. So the entire row of zeros. So we have to make that in a different form. So we need to form a new polynomial, which is called the auxiliary polynomial. And PS is actually determined by looking at the row above the row where you have your entire row of zeros. So you will look at this polynomial. The PS is then as follows. PS is then 7s to the power 4. Why? Because this is the coefficient of the s to the power 4. And this is the coefficient of the s to the power 2. And this is the coefficient of s to the power 0. So you actually go with two orders in sequence. So you have the 7s to the power 4 plus 42s to the power 2 and plus 56. Now, we need to determine the new coefficient for this row. What we do is we differentiate the PS, as you can show here, and this is just 28s cubed plus 84s plus 0. I've just purposely put this 0 here that you can see how we replace these three zeros here. Now use the coefficient of this expression and replace this. So I replace that is the table. So I make it the red. You see here 28, 84, and this is just 0. And I will now carry out the analysis using this table. So if I now copy this in the next sheet, again, this is the general table, and I have now my new table using the polynomial PS. I continue with the C1 calculation, which is shown here, step by step C1, C2, and C3. Again, they're very familiar formulas we have used also in the previous videos. Now, I can carry out the calculation for D1, D2, and D3. So these are given here, D1, D2, and D3. Okay. Now, again, I need also the E1, E3, E2, and E3 here. Let's do it also. E1, E2, and E3. Now, we have now the necessary elements to substitute the values in the row table. So let's do that. I have now set all of the values in here. Which you see here, if you look at the first column, check the first column for stability. we see that there's no sign change at all. It's almost all positive, 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 positive. So you have 6 entries which are all positive. That means the conclusion is actually we see no sign change. There's all 5 roots, because it is a 5th order system, are in the left half plane. And since we have no roots in the right half plane, that means that the system is stable. This closed-loop system is stable. And that is actually the way how you can solve the problem where you have a row with entire row of zeros. Now, we have now discussed several examples using where we have the case 1 and using also the epsilon method and also the reversed order method or reversed coefficient method. So let's verify our calculations using the simulation in MATLAB. So I have developed here a script with our examples, the transfer functions, and also I have here put the 2 transfer functions I have discussed in the general overview. So let's run this first before we work out the analysis. So we have now the script running here. So I have now all these elements collected. The T1 is actually the transfer function, the closed transfer function for the example 1. T2 is for the example 2 and T3 is for the example number 3. And this is just an extra example when I also want to discuss some more topics in more detail. So what I can do is I can check the stability condition for these 3 closed loop systems. What we have discussed for the transfer function T1 for the first system is that the system was marginally stable. So let's verify this. Let me first type in T1. What you can see is this is the transfer function, and which is exactly what we had in our example. I can also make a nicer view using this command. T1 is zpk and then T1 again. That makes the transfer function look like a 0 pole gain configuration. So it's much nicer to see the poles. So if I now look at the transfer function now in this form, I see there's a pole at minus 0.333. So it is actually a stable pole, but this will create s squared plus 2. If you just, of course, equate that to 0, you will have a pure imaginary pole here, 2 imaginary poles there. So that's a complex conjugate pole pair. That means this system will cause, of course, sustained oscillation. Now, we can also check that in the pole 0 map. You can do PZ map and then T1, and you will have your plot here. Now, as you can see here, if I now make it a little bit larger, I also put the grid, you can see that this is these are the 2 complex conjugate poles. Of course, if you make s squared plus 2 is equal to 0, you will get s squared is equal to minus 2. So you will have s is equal to plus j squared root of 2, and the other one is minus j squared root of 2. That's actually what you see here. This is approximately square root of 2, at 1.41. Now, in a similar case, you have it's paired, and you have the real pole at minus 0.33 or 333. So we have now actually checked the situation also in the pole 0 map. We can also check this in a step response. So let's make a step of T1. And you will see that this indeed produces an oscillation at the output. So if I just a little bit zoom in this part, you can see that this is indeed a nice similar oscillation. So this system is marginally stable. It is not unstable, but it is marginally stable at the edge. So we have none of the poles are on the right half plane. That's actually for this situation. You can also check this using another command, pole, the location of the poles. You get a numeric value. This will result, PZ map will give you a graphical view of the poles and also the zeros. And this will result the poles in a numerical form. So if I now type in pole and then T1, you will see that there is a complex conjugate pole pair, which these two. As you can see, there is no real part, pure imaginary, and there is a pure real pole in the third case. So we have now checked that this is indeed marginally stable. Now let's move on with the next example, which is the T2. So if I now type in T2, which is this one, this is what we have discussed. If I now do T2 again and then looking nicer with the ZP key command, I have the following. Now, as you already can see from this, I can see that this has a -2 as a real pole, which is stable, but this is a +1, so it is already an unstable pole, and I have two of them, so it's already unstable by looking at the transfer function in this factorized form. Sometimes, of course, it's really hard to factorize this into this, so you have to sometimes analyze this in a different form. But if you look at it already here, you can already say the system will be unstable. Now let's check this again in the PZ map. So the T2. Then I have now produced my plot here. So what you can see is we have a, let me check this. So we have a pole at +1 exactly. And we have another pole at -2. This is a stable pole. This pole is actually a double pole. It's not really clear here. So if I now do pole T2, you can see all of the poles. You can see -2, which is a stable pole, and you have two poles at +1. That means actually the system is for sure unstable. Again, we can check that using the step T2, and then you can see that this system is indeed unstable. It goes actually out of control. Okay, so let's now check the situation for the third example, T3. If I now type in, this is the fifth order system. We have discussed this, and we've concluded there that the system has no no right half plane poles. So the system was not unstable, it was stable. But let's check this, verify this. So let's make it again. T3 is again looking nice with the ZP key command. So I have now this transfer function looks much nicer than this one, I think. So you have a -7 here as a real pole, which is a stable pole. But I have now a s² + 2 term, which is again producing a complex conjugate pole pair, so pure imaginary. And I have another complex conjugate pole pair. And this produces actually two frequencies. And that will cause, of course, the summation of these frequencies together, so that I will get, in this case, also a marginal stable system. It's not unstable, but it's at the edge, so it's a marginal stable system. I can see it also from the pole. Just type in pole T3, and I see there is a pure real pole, which is a stable pole, -7. And I have now two poles, imaginary, at +J2 of I2 and -J2, which is the result of this term, and I have now also two imaginary poles due to this term. So this will result actually a summation of two oscillations. So the PZ map, let's look at the PZ map for T3. This is actually the following, and what you can see from here is the real pole is here, that's the stable pole, -7. This is the pole at -2J or 2I. This is of course a very small number for real part, it's just a numerical error. And the associated pair for that one is shown here. This is a +2J. And I have now here the square root of +2J. That is actually the following. And the -J times the square root of 2. So this is actually the associated pair. So this is a pair and this is a pair. But you have now two oscillations together. So that will be a effect superposition of those two signals. That means if I now do the step, so this is interesting, if I do the step T3, this will of course produce also an oscillation, but this is not a really nice pure sinusoidal output signal. But if I now zoom in, you can see why that is. You can see that this is a summation of two signals. You can of course work this out using Fourier analysis, etc. But that's not the case here. What you see is that this system is for sure not unstable, but also at the edge of stability, so it is the marginal stable. So we have concluded actually, based on a table, that this system was stable at all its poles at the left half plane. So what you see is here in this example, that it's always required and necessary step in your analysis to check this using a simulation. Because if your system is, for example, fifth order or higher order, sometimes you can maybe lose the the details out of it, and that is actually the way to check your verification, so check your calculations. And now we have checked this. It is not completely unstable, but it is at the edge, and you have now seen in this example. I hope this clarifies the situation in more detail using this simulation part of this video. So we have done in the first part several examples, and also I've worked out example number 2 in different two ways, in the Epsilon method and also on the reversed coefficient method. And I've seen now here that the transfer function T3 shows a margin stable system. So we have now also verified all of the aspects in it. Now, I can of course check also T4. This was just an extra example. You can just type in T4. I just do it directly at the ZP key form. You can see here that there are two poles, actually real poles, which are stable, but it's an unstable part. And this is just an oscillation again at plus J5 and minus J5 that will cause a pure imaginary pole pair. Now, if I do here, of course, the pole and then T4, this will of course produce for sure the unstable part, because you have a root at the right half plane. This is of course the problem. If I now do step T4, you will get of course a response which is going out of control. And this was just an extra. I haven't calculated this. I haven't discussed this in more detail in the calculation, but you can see that there is a way to do it also in MATLAB. Okay guys, it was again an extended explanation with using a lot of examples and calculations, and also the simulation in MATLAB that will of course confirm our calculations in this form. Thank you very much again for your attention. If you have questions, comments, suggestions, please let me know, and we will keep in touch and see you next time in another video.